there's a limit to it. So it's not that the two are additive. If you add CO2 on top of food deprivation, you don't get an additional metabolic suppression. So if you control for the effect of body size and you get an average for all the different CO2 concentrations, or a mean rather, a size normalized mean for the different CO2 concentrations, and plot it, you get something like this. In 2008, we only did 2 CO2 concentrations. They were both low and similar to animals that were starved in 2007, that we starved in the laboratory. And then the effect of CO2 on fed animals in 2007, higher CO2 led to lower metabolic rates. So this is natural variation in this Antarctic region. During the austral summer, you get phytoplankton blooms, you get very low CO2 and high pH, up around 8.4. In the austral winter, it drops to about 8. The target CO2 that we were using in the lab, the control was about 8. So our control was as low as they ever see naturally, and our treatment was much higher. So it'd be interesting to see what happens if you crank the pH up or the CO2 way down. And I'm going to end with one more short story. A former student of mine, Amy Moss, who's in Bermuda, looked at animals that naturally migrate in the eastern tropical Pacific into an oxygen minimum zone where there is also high CO2. So this CO2 level is as high as the treatments that we were using in Antarctic. And some species of pteropods are migrating down to these depths in the eastern Pacific where the CO2 is naturally very high. The species that do migrate into that low oxygen, high CO2 showed no effect of CO2 on metabolism. We had these 3 species were all unaffected by CO2. The one species that didn't migrate, that always stayed shallow above that high CO2 zone, did show a metabolic depression when we exposed it to CO2. So take-home messages, we definitely need long-term studies to figure this out, whether how food availability changes over many years. Add to that natural variation in CO2 and temperature, oxygen, and food availability. There are going to be interspecific differences in the response to all of these variables, as well as what may be just population differences. And then there's acclimation versus adaptation, where we haven't really had a chance to look at that. But the temperature effect tells us that the Antarctic species with the extra mitochondria they generated, because of that extra mitochondria, are unable to tolerate higher temperatures. And the temperate species, when we put it to 0 degrees, just stop swimming entirely. So there's definite adaptation there, and those 2 species cannot cross the circumpolar current in either direction. So I will take any questions. Hi.
So I was wondering, when it comes to, I was wondering if you think there are any interactive effects in terms of perhaps where pH makes it, lower pH makes it hard to pick up oxygen, but also might make it easier for them to attack their prey if the shells are thinning on their prey items. Have you investigated that at all?
We haven't. It's something that we've wanted to do. Because of that unique feeding system, it seems like you could tease that apart. Either the shells are thinned and easier prey, or the prey is more sluggish and can't catch them, or there's definite interaction. So you could hold the prey but not the predator in high CO2 and then stick them together and see what happens. I don't know how you would get it at exactly, but yeah, I think you could. There definitely are could be some interactions going on there that we haven't had a chance to look at. Kendra.
I've forgotten Amy's study in the eastern tropical Pacific that high PCO2 water was also very low pH, about 7.3. Did she see any evidence of shell dissolution? I know they were migrating.
I don't think she had a chance to hold them long enough to look at that. It wasn't obvious I don't know if she looked at it systematically, but it wasn't obvious catching animals shallow water daytime versus deeper, vice versa, shallow water nighttime and daytime deeper. We didn't see any obvious differences, but I don't think she looked at it systematically. So, she's definitely seen dissolution in the animals I mentioned that she's holding over many generations. She's seeing dissolution effects fairly quickly in those specimens in high CO2. All right,
Well,
thank you.
I have a very simple question.
Okay.
I know nothing about this pteropod.
I'll give you a very simple answer.
Okay. But I found that fascinating, how they flip their wings.
Mm-hmm.
One or twice a second,
Mm-hmm.
2 hertz. So what is the highest possible frequency these animals can flip wings?
That's a great question.
In the ocean, I mean, in the air, maybe the blooming birds, hummingbirds, right? Maybe it's a couple of hundred hertz.
Yeah.
It's very fast.
Yeah.
Because
So
the
in-
resistance is so different. So do you
it
have a
is.
number?
I don't have an exact number. So that project involved a collaboration with a biomechanist named Robert Dudley at
Yeah.
UC Berkeley. And he only ended up working on the shelled species. No. Yes. No. I don't know. I'm confused now. And he was there at a different time of year. He was unable to go at the same time. So what he ended up working on were the Antarctic, the transition from the larval period where they swim with cilia to when it becomes better to use wings. And there's definite, it's definitely controlled by biomechanics, the viscosity and things like that. The fastest I've seen pteropods beating is in the tropics when we're blue water diving. You can see them. And again, this is just casual observation. It's definitely 4 or 5 up, and I've read as much as 10 hertz, but none of those are really verified with high-speed videography or anything like that.
So you mentioned how the feeding is kind of coupled, like the species almost like, it almost seems like it co-evolved to one feeds off the other.
Mm-hmm.
Is there almost like a positive feedback loop where the lower or the higher CO2 leads to lower metabolic rate in the one species, and that metabolic rate is also lower in the other species, but there's like the one species can't survive enough, and that
Yeah.
also impacts the other species? Like, is there this kind of interplay there?
Yeah, like a predator-prey arms race, they call it, where so you can definitely see that in pteropods in general, where a species becomes modified to catch a particular species of prey. And in the Antarctic, where they've lost that burst swimming ability, the prey species has also lost it. We've not looked at the mitochondria and the nerves in the shelled prey species, but they definitely don't have the same burst ability either. So if they hadn't lost it, if they'd have evolved a way to keep burst swimming, presumably the prey species wouldn't be able to keep up with them. So yeah, I think there's definite interactions going on there.
Well, thank you.
Thanks.
So moving forward, we're going to have Professor Boris Gaprin talking about physics. All right. Put it in your pocket.